this is gonna be like basically the end of the first half of the course, which is about how to build the, all these structures that is powerful in like we show the existence first, and now we just see the fast algorithm for this thing like tree-flow Sparsifier. And the next part of the course is gonna be about showing how to compute MaxFlow. Like this part is about like assuming MaxFlow, how to get a lot of good things. Next part maybe is about how to get MaxFlow fast. Yeah, and it turns out that the structure that we have built, like tree-flow Sparsifier itself, will be useful for building fast MaxFlow again. So it's like a really crazy feedback loop. Anyway, but before we go to the next part of the course, we finish with this last one. And maybe next week, I will teach. I will not give a new thing, but I will maybe survey the whole area, what's actually going on, and like maybe point out again like what is a good question to try for the project. Yeah. Okay. Good. So for last class, right? We basically show a fast construction of boundary separator expanding hierarchies. Okay. But the quality, the approximation that we get is not so great. It's something like log n to the square root log, which is n to the little one, but it's not Polylog. Okay, and depth is root of n. So once you get BSE hierarchy with this approximation, you basically get tree-flow Sparsifier with this approximation. Yeah. Just this thing times this thing is still this thing. This times this, get this. Okay. So it's a good and fast tree-flow Sparsifier, but not Polylog quality. And today we're gonna get it with Polylog. Okay. But how do we do it? We will basically bypass the BSE hierarchy. We only know how to build tree-flow Sparsifier based on BSE hierarchy, but today we're gonna not use it. Yeah. We're gonna show another way to build it. Yeah. Okay, and so this is a lecture based on this paper, more than 10 years ago, actually. It's a really cool paper that I spent years to understand, actually. But at least now I can explain it. Yeah. Okay, so the way that we're gonna build this is gonna be top-down. Okay? And I'm gonna first describe how to construct some hierarchy, and then from the hierarchy, it will define the tree in a natural way. Okay. So first, let's see how to construct the hierarchy. Okay, so just to recall, we're gonna construct a hierarchy of clusters, which is like usual. This cluster is just an induced subgraph. And the root cluster is just the whole graph. The leaf clusters correspond to vertex set of the input graph, just like usual. Okay. And we're gonna construct all this in the top-down way. Okay. So meaning that like I just gonna start with some cluster, and I just gonna try to define what should be my children clusters. So suppose that H is a cluster. Okay. If H is a singleton, it has only one node, then you don't need to do anything. So only when H is not a singleton, then we're gonna construct the children of H in this way. So, okay. This is a way. Okay. So first, let's say that this is hash. Okay. Now, the first thing that I'm going to do is just to compute expanding balance separator. And maybe think of phi here as 1 over log square. So we know how to get the expanding balance separator fast now, right? We show the slow algorithm that the expansion is like 1 over 4, but we actually show a way to build this when phi is like something like 1 over log square fast. Okay, so this is like, let's call this f in, as in like inner separator. Okay? This is gonna be just some balance separator that is expanding in hash, okay? And call this inner separator. Okay, then next we're gonna compute outer separator. So what is this? This is going to be the min cut, okay, in hash. That's basically this, where the source is f in, the node weighting of f in, and you can think of this as like the hz itself too. Like, so by now I think you might know that like when I look at the node weighting of some h, I just think of it as a hz. Okay. So this is like the source is just the f in, okay? And the sink is just the boundary of hash, which is this guy. Okay. Okay. But this boundary here, I scale it down by something like 1 over log. Okay. So just think like we have the source here, and the sink is the boundary of hash, and we want to compute min cut between them. Okay. Or you think like you try to send flow from the green thing to the purple thing. Try to like send max flow. Okay. And if you can send flow successfully, then you would be basically done, but you might get stuck. For example, so this is like there might be min cut that separate them basically. Okay. So what you get basically is something like this, right? Like this is the min cut, so there is always some flow here and flow here. Like maybe let's focus on let's focus on this part. Yeah. Suppose that there is no separator, there's no boundary here, right? Then you're gonna get basically there is basically you think of you compute max flow from the purple part to the green part, and there's gonna be the flow before min cut and the flow after min cut. We have seen this, and what's the flow before min cut? It's just a flow that like the flow such that everything here is kind of send 1 over log. At most 1 over. Actually, you should think like this. The flow before min cut, the flow on this side, right? Basically, each of these send 1 unit. And each of these guys receive at most 1 over log. Okay. Maybe some of this thing don't get the flow, but everyone here is saturated. Like the edges along the min cut is saturated by the flow, right? Like, and send it to the, so there is a flow that saturates this part and respect this part. Okay. And this part has only sink capacity of 1 over log. Okay. Another side is also that for the flow on the right side, you also have that there is a flow that saturates the cut. So meaning that everything here send 1 to some guy. Okay. And this guy receive 1 at most. This one will send 1 over log. 1 over log. 1 over log. 2, yeah. Okay. And similar thing happened here, right? Okay. Is the picture clear? Like that was the structure of F out, the outer separator. It's just the min cut that separate F in from the battery. Okay? And so what you know is just that from F out, you can saturate the flow from edges of F out to both directions. Okay. Okay. And then, how do we define the children of H? The children of H is simply connected component after you remove F in and F out. So it's going to be this component, this component, this component, this component, and this one. So that's how you define the children of the cluster. And once you define the children, then you recurse to the recursively build the children of the children and so on. Okay. Question about how do we build the children of any cluster? Good. Okay. So that's how you can define the hierarchy in the top-down way. Just start with a whole graph, compute F out, F in, build the children, and recurse. That's it. And that basically defines the tree. Okay. So how do we build a tree? We build a tree from the hierarchy in the same way, in the natural way. Okay. Which is, look at a hierarchy H. There is a parent hierarchy, the parent cluster. Sorry, the cluster H. There is a parent cluster, H parent, which is, yeah, like this. If this is H, then this whole thing is H parent, right? So for each cluster H, we just create a tree node here, UH, and connect it to the cluster of the parent, the node of corresponding to the parent cluster. Okay, and the capacity of this edge is going to be just the cut size, which is like the battery of the cluster. So this is capacity here is just the cut size, the battery of H in G. Okay. And you do this for every cluster, and that will give you the tree. This is the same construction. This is the same construction when we define a tree from the BSE hierarchy, if you recall. Okay. Question about how we construct a tree? Good. Okay. What's the depth of this tree? log n. Why?
Because of we're doing it with expanding balance separators, so it's each.
Exactly. Yeah. Even if we define the children only based on f in, it would be log n depth already, because every component that f in separate have size less than half. But here we even do it in a bit more fine-grained way, which is we refine the component a bit further. Like we have this red component that refines some component a bit further. So this is log n depth. Okay. So this is tree with log n depth, log n levels. Okay, because f in is the balance separator. But here is a main theorem. I claim that this tree, T, is a tree-flow specifier of the graph, where the quality, the approximation, is the number of levels times log n times over phi. So if you contrast, like when we build it, the one that is based on BSE hierarchy with L level, from that construction, when we build a tree, we get a tree with quality something like L over phi. Okay. But this one is like L log n over phi, a bit worse. But the thing is just that, just currently, I don't know how to build BSE hierarchy fast. So if we know how to build it fast, we could have just get this fast. And today, I'm just going to show you how to build the tree directly without BSE hierarchy with this a bit worse quality. Okay. So that's a claim. Just build the tree is just built in this way, quite simple, and that's the quality of the tree. And from here, we immediately basically get that it means that we can construct a tree-flow specifier of G such that it has this many levels, and the quality is log to the fourth with high probability. And the running time is something like Polylog minimax flow plus nonlinear term. Okay. This is the max time for computing max flow. So why is that? Well, because from previous lecture, right, we know how to compute expanding balance separator in Polylog max flow time. So specifically, we can compute the F in, the balance separator F in, okay, where F is something like 1 over log square expanding. Phi here is 1 over log square. And the running time is something like log square minimax flow. Just this log square is just really the number of rounds from the card matching game, where we use the version of the card matching game where we have deletion and transferring vectors. Okay. So Fin can be built in this time. But how to build the whole hierarchy? Well, like we basically compute F in, and then one more max flow calls to compute F out. That's the running time for one level of the hierarchy. There are log n many levels. So the total running time is just this thing times log n. Okay. That's why the running time is something like this. Just this times log n. Because we just do this and one more max flow calls. Okay. What's about the quality that we get? This is just basically just from here, where L is log n, and this thing is like phi is 1 over log square. So in total, this gives you log to the fourth. That's why the quality is log to the fourth. Okay. And we only have this with high probability because F here, F in here, is expanding only with high probability. Okay. Good. So if you believe in theorem 1.1, then we get fast 3-flow Sparsifier with quality log to the fourth. So the rest is about proving this main theorem. Okay. So let's prove it. Any question before I start proving? Okay. So now the goal is just to show that the quality of this tree that I define in this way, the top-down way, has this quality, L log n over phi. So just to recall again, what does it mean to say that the quality of the tree is Q? It just means that, anyone recall actually, what does it mean to say that the quality of T is Q? Okay.
A degree G respecting demand that is routable in T is routable in G with congestion and post Q.
Exactly. Yeah. And also another direction too.
If it's routable in G, it's just routable in T.
Exactly. Good. So it preserves routability. Yeah. The first direction is that if this degree respecting demand D is routable in G, then it's routable in T with congestion 1 as well. And another one is if it's routable in T, then it's routable in G with congestion at most Q. Okay. So now I want to claim that this first direction is not too hard to see. If it's routable in G, then it's routable in T. And this actually is easy to prove, and we saw the proof before. So why is that? So we know that if D is routable in G, right? Then if we look at for any cluster H, let's say that you have a graph and you look at the cluster H, okay. Then you know that the total demand that this demand try to route from inside H to outside H. This is going to be at most the cut size of H. Otherwise, it cannot be routable in G. Okay. So this you know. But we also know that the capacity of 3H correspond to the node, the 3 node that correspond to the cluster H, to its parent. We just set the capacity to be this much too. Okay, so we have this graph, then we have the tree that kind of correspond, like the 3 node UH, where like maybe the leaf of the subtree here have the leaf on V of H. This is V of H, right? So now the 3H here that go between this to its parent, this capacity is also the cut size. This is at most the cut size. So the total demand out of this hash is at most this much, the cut size. So it means that the total demand, the way to route, the total demand that try to route demand out of this guy through out of hash to outside, it will go through this guy. Yeah. We only try to route flow between the thing outside, like the only flow that will, okay. When we try to route flow, the flow will go through this edge, 3 edge, only for the demand that, only between the demand inside hash and outside hash. Okay. But we try to route at most this much. And that's at most the capacity of this edge. So that's why, for every 3 edge, the congestion here is at most 1. So we saw this kind of proof before already. And okay. So I claim that the congestion on the tree is at most 1. Okay. So the goal is actually then here. If there is a demand that is routable in T, then we try to route it in G with congestion Q. Okay. So the rest of the class is for proving this one. Okay. So now let me give some more terminology. Okay. So think of this hash as maybe level I cluster. Okay. So I will call this, there are several children of hash. The red one, I call it outer child, outer children. The red one are outer children. The green one here, they are inner children. Okay. And now I define one more thing, which is the core of the cluster. So the core is basically the union of all the induced subgraph by the inner children. The subgraph induced by the inner children, which is just this green thing. So when you remove the outer children, that's the core. Okay. And F is inner separator, F in is inner separator, F out is outer separator. And yeah, the inner child, basically they are incident to F in. The outer child, they are not incident to F in. They are only incident to F out or the battery of hash itself. And the core is just hash after you remove all outer children. Okay, good. So now, our strategy is here. We're gonna do bottom-up routing strategy. What I mean is here, we have some demand D that respect the degree of G. And this demand is, you can route it in T, in the tree. We try now to build to show how to route it in G. Okay. And we do it in a bottom-up way. This means that, and by bottom-up I mean here, it's similar to how we show this in the, when we show how to build tree-flow Sparsifier based on BSE hierarchy. Okay. But the bottom-up way is like this. So we build, we look at each cluster from the bottommost level, right? And then try to route, try to build flow partially from the bottom cluster, and then go to the next cluster, go up, and try to send flow further from the next level, and so on and so on. And this flow will be such that when you concatenate all the flow from bottommost level up to the top level, it will, when you concatenate all this flow, it will be the flow that route the demand, D, the original demand that we want to route. Okay, so let's be more specific. Okay. So what I mean is here. So suppose that wait. 1 second. I think okay. Good. So, wait, there are, okay, good. We have the demand D that degree G respecting, right? And the final goal is to route this demand D. Okay. But now let's say that focus on the demand pairs DH, such that it's just the demand pairs where at least one endpoint is in H. Okay. So it can be demand between A and B, where it's between H like this, or it can be demand between A and C, which is the one inside H and another one is outside H. Okay. And I will assume that I have done work bottom up, meaning that my children kind of take care of the routing up to some point so far. That is, I'm going to assume that we have partially route this demand to the boundary edges of children. Okay. So for example, if I have demand to route from A to B, suppose the demand is from A to B, okay, then I assume that I have done some work on the children, and I might have sent flow up to this point. Yeah. So the flow kind of is sent and it stopped at the boundary of the children. So the goal is to get some flow path that connect maybe from A to B or from A to C. That's the goal. But I have partially routed the flow path and it stopped at the boundary of the children. Okay. This guy, I might also have sent some flow and it maybe stop here. Okay. So the goal is maybe the goal in this level is now to connect the flow path so that it is routing between A and B, or the goal is now to try to go further to C. But actually, if we want to go further to see, we will just try to send flow to the battery of H. So the goal is always like either intuitively just try to finish some demand inside, or just otherwise, if it's a demand to outside the cluster, just send up to the battery. Just send the flow, like kind of build the flow and stop at your own battery. And okay. And I have some more promise. That is the flow that is routed by the children that kind of stop at the battery of the children. Okay. Each of these battery edge here receive the load of at most alpha I. And think of alpha I as some constant, but it's not 1. It's less than 3. It's at most 3, but it's not 1. Okay. So what I mean is that, like, I may have another demand here, and this guy might try to send flow like this. Okay. And basically, although this edge has capacity 1, the total flow that try to send to this guy is at most alpha I. So it's a bit more than 1. Can be a bit more than 1. Okay. Okay, and now the goal that we need to achieve, that we need to do inside the cluster H, okay, is kind of to further route this flow path from that has been done so far from the children, and the routing should have congestion at most like log n/5 inside H. Okay. And I have 2 goals. My goal is that any demand pairs between 2 vertices in the core will be successfully routed. For example, if it's between A and B here, I want to basically kind of connect the flow path so that basically you get the flow path from A to B. You finish the routing. Okay. So if it's between things inside the core, finish it. Otherwise, if it's the demand pair not between vertices inside the core, I will just forward it to the battery. So every other demand with one endpoint in H, you just try to partially route it to the battery. You don't try to finish them, just route them to the battery. So, for example, maybe, the flow that I try to route to C just send to the battery here. Maybe here I just try to send to the battery further. I try to send flow to the battery of H, right? Not just here. Yeah. So if I have some demand, I don't know, D and F, I just try to send to the battery. Okay. Something like that. And we also have that each of these battery, it will receive the load of at most alpha plus 1, which is a bit more than alpha. So it's more than alpha, like this is like alpha plus times 1 plus 1 over log, basically. So just a bit more. Okay. So suppose that I can do this, okay, with low congestion. And do you agree that we will be done? As in, once we just concatenate all the flow from the bottommost cluster to the top cluster, then this concatenated flow will be the flow that routes the original demand D.
Wait, sorry, how are you handling the case where one of the endpoints is like in the green part and the other is in like a red cluster?
Yeah. We will just forward it to the battery.
Okay.
So that's not so intuitive. So that's important point that I will talk about soon. That is, if it's between A prime and B prime, even though they are just both inside H, I don't try to route them. I just forward it to the battery.
Okay.
Yeah. Yeah.
So is this like this high-level algorithm is like kind of similar to like the previous way we constructed a tree flow Sparsifier?
Yeah, it's quite similar. Yeah.
Yeah, we also have like this induction where you just like assume that where you just like go to the next cluster, you just set it up, and then you just set it up again.
Yeah.
Is the idea behind just forwarding to the boundary in between those, like the core and the outside or outer? Just that, like, because we can't really route across the min cut necessarily, so we
Very
need to
good.
forward it to the boundary, and then it gets like there are other edges that can.
Yeah.
Then we can bring it back.
Exactly. I will go to this point very soon, but exactly that's the intuition. Like, it could be that there are many. I talk about that soon. Yeah. But my point is like, if we either finish the job inside the core or just forward to the battery, if we keep doing that, well, at the end, at the top level, there is only the core. At the top level, there is no that at the top level, the top cluster, there is no battery edges, right? So there is no outer children. So there is only the core, and we will finish the job inside the core there. Okay. So at the end, when you concatenate out the flow, you route the whole thing. Okay. So here is the important point. Some of these demand pairs that we just route to the battery, they are also between vertices inside H. So that's quite counterintuitive, but we will see why we need this. Okay. Okay. Yeah. They are inside H, but yet we just route them to the battery. We can have just delegated to this task to the parent cluster. And this is necessary. This delegation for this construction is needed. It's crucial. Why is that? Okay. Because imagine that you have maybe like A1 up to, I don't know, AK, and maybe B1 up to BK. Or maybe C1 up to CK here. Okay. Imagine that you want to route between the AI to BI. Okay. And you only try to route inside H. Don't even go out. The flow path don't go out of H. It means that you need to go through this min cut edges. But there is no guarantee that this min cut edges is big enough. This cut maybe is tiny. So then this routing will cause large congestion that we don't want. Because maybe the correct way to route is to kind of go in this way. The correct way to route with low congestion maybe not to go through this guy. Okay. Similarly, if you want to route maybe between A and C, between outer children, you don't want to go through the min cut edges. You might need to go out. Okay, so you see for this construction, some of the pairs inside H, it's just better to forward it to the boundary. Okay. I want to contrast this a bit with our previous construction based on BSE hierarchy. There, we complete all the demand pairs inside H. Like every pairs inside H, we route it and finish it inside H. Because there's no such bottleneck, there's no red bottleneck like here. Because we know that for BSE hierarchy, like both separator and the boundary of H, they are expanding. There's just no bottleneck between them. So we could have just route them and finish it inside H. But this is different. Okay. Good. Okay. So now, okay. So assume that we can solve this above routing tasks inside each cluster hash. Then yeah, I hope you see that like given any degree respective demand, we can route this demand D in the bottom-up way just by concatenating out the flow. Okay. And the final concatenated flow will route the demand. What's the congestion? What's the total congestion at the end? After you concatenate all the flow.
It's going to be like log squared n over phi.
Log square n over phi. Yeah, exactly. Why?
Because each layer routes with log n over phi, and we incur a hit because of the log n.
Exactly. Yeah. Like the routing on each level, they are disjoint, right? We route in each layer. We just route with congestion log n over phi. But we always route inside the cluster, or we just finish at the boundary. So in total, in one level, it's just 1 over phi. Like there is no interference between cluster. But then there are log n many levels. So the total congestion is just log n times log n over phi. So that is L, the number of levels, times log n over phi. Okay. Also, this load, okay, the load that you can forward to the battery at the ith level, that's like alpha I. I claim that this is going to be just 1 plus 2 gamma to the I. Why is that? Well, and this is going to be less than 3. Yeah. So, because at the bottommost level, when the leaf cluster is just a singleton node, and you just need to route to someone else from V, you can do this just by basically kind of route to the incident edges, and you know that you want to route at most, like this is you want to route at most degree of V in total. The total demand out of V is the most degree of V. So sending this kind of almost trivial flow to the battery, this is just congestion 1 at most. Okay. The total capacity is degree, and you try to route at most degree. Okay. So the load that kind of the battery of this trivial cluster get is at most 1. Okay. But then for the next level, we promise that alpha I is just at most this much times alpha I minus 1. So just unfolding this thing, you get 1 plus 2 gamma to the I. So this is just by induction. But then it means that for all level L, alpha I is this, but what is this? This is at most e to the 2 gamma log n. But we set gamma here to be 1 over like 2 log. So this is at most, this is just at most e. This is just e, which is less than 3. Okay. So that's why I set gamma to be 1 over log. I want to control that the load here, although it can accumulate a bit, it's just always at most a constant. Okay. So now I just need to try to achieve this goal inside each cluster. Okay. The goal is 2 things, right? To finish routing inside the core, and the rest forward to battery. We need to do these 2 things with low congestion. Let's do the first thing first. So finish routing inside the core. Okay. So consider the demand between vertices inside the core, or the demand between vertices inside the core. We want to route all these things with low congestion. Okay. So what do we have here? We have that maybe A, B, C, D, okay, E, okay. Everything has been, so far the route to, they have been route to is the battery. Okay. You have route them to the battery. Like each of these children, each of these inner child, they route the flow path so far to an end at its own battery. And each of these has load at most alpha I. And let's say we just want to finish the flow path. We want to finish this demand. Let's say we want to route between A and B, and maybe this is D. Maybe between C and D. And I don't know. Just route between them, okay? We need to finish this routing, connect them. Okay. So trying to basically connect from the battery here and try to connect them. Okay. That defines the demand inside the core, which is we just say that, okay, from at this endpoint, maybe we try to connect to this endpoint. That's just some demand between the battery. So this task, okay, define one demand. Let's call it D complete, which is to complete the routing inside the core. Okay. And this demand will respect the battery of inner children, just because it's the demand between the battery of inner children. But when you scale it up by alpha I, just because the load there, it's not just one, it's alpha I. Okay. So it's just some demand that try to route between this thing, between this thing. Okay. Why do you think that we can route any demand between the boundary of inner children with low congestion? If it's just the demand between F in only, do you agree that we can route with low congestion? Yeah, because F in is expanding. So any demand between F in would be you can route with low congestion. But now it's not just F in. It's also the boundary here and the boundary here. Okay. Yeah.
But we also have like the min cut that define that, so we know all of that stuff is routable with congestion like log n.
Yeah, exactly. Like, so F in, first of all, F in is expanding. This guy is expanding. So that's good. But what do we know? We know that all this boundary here, there is no bottleneck. There is no bottleneck that this guy can send to F in. If there were the bottleneck, there would be like some other children. Like there would be some red cluster. But we know that like we have computed max flow between this guy and F in, and there's no bottleneck. So we know that actually all this edge can send flow to F in. All this guy can send flow to F in. Right? So it's like, so I claim that if F in is expanding, and this boundary of the core can send flow to F in, so the union of them need to be expanding too. Okay. So that's why you should get this intuition that any demand between the F in and the boundary of the core should be you can route demand with low congestion. Okay. So let me try to be precise. So let's try to route this demand with low congestion. So again, first note that this boundary of all inner children is just basically consists of F in and the boundary of the core. Okay. But I claim that F in union with boundary of the core is something like gamma phi expanding. So it's a bit worse than phi expanding by log n factor. Gamma is like 1 over log. So why is that? Yeah, and if you assume this, you are done. Then if you assume this, then this demand that try to complete the demand inside the core, you can route it with congestion this much. Okay, like this thing is just from here, but we need to pay another alpha I here. But this in total is just order of log n over phi. Okay. But we need to prove this. We need to show that the boundary of the core and F in, they are together expanding. So, okay. So, okay. First, we know that F in is phi expanding. Okay. And now the flow, there is a flow from like, yeah. Okay, delete. Okay. We know that each of these guys can send 1 over log flow to this to F in. Each of this guy can send one flow. This guy send one overlock to F in. This guy can send one and one. And this is again one overlock. Yeah. Okay. So the part from F out here can send one flow to F in. The battery of H can send one overlock flow. Okay. Are we good here? Like the purple edges can send one overlock flow to F in. The red one can send one unit of flow to F in. Okay. And this flow, the blue flow to F in here, have congestion just one, okay? Because it's just the max flow from the feasible flow from these edges to F in. Okay, so this is the red one, the red. This is the purple one. Yeah, and there is a flow that saturates. This red one and purple one to F in the green thing. Okay. And this thing has one, this is like one overlock here. Okay. So this just means that like there is a flow that saturates all the battery of H after I scale it down by log. Because if I change this from 1 to 1 over log, this is just like of gamma of H core. So I can even saturate without 1 over log here. Okay. So there is a way to saturate from the battery of H core after scaling down by log and send it to F in. Okay. So now if F in is expanding and I can send flow from the battery of a core to F in, then the union of them will be fiber 3 expanding. Why is that? This is basically kind of just from the homework that you have shown. If something is an expander, and then you union the meshing, like you union the meshing to the expander, then it's still an expander. This is the expander, this is the meshing. Okay. Make sense? So I take this as exercise, yeah. But to convince yourself. But if this thing is phi over 3 expanding, then like if I also just say I scale this down by gamma 2, then it means that this union F in gamma is phi over 3 expanding. So it means that this thing is gamma times phi over 3 expanding. Okay, good. So are you convinced now that the demand, like we can finish the demand inside the core with low congestion? Just because this is just to finish the demand inside the core, this is just some demand between the battery of the core and F in, but this set is expanding in H. Okay. Just 1 second. Note that the routing might actually go out of the core, right? This is just expanding in H. But so we don't route inside the core, but we route indeed inside H. Okay, Sam.
Wait, sorry, maybe I'm missing something obvious, but how do we know that Fn is a matching?
Oh, Fin is not a matching.
Oh, okay.
Fin is like expander because it's an expanding set.
Okay. I see. Right, yes, okay, good,
Yeah.
yeah. Great.
Fin is kind of expanding, and we have kind of matching from battery of the core to the expander.
Yes.
Okay.
So the matching comes from the computation of like this L flow, right?
Yeah, exactly.
Okay, so is there a generalization if we instead allow like arbitrary weighting, so like not like the L flow, then you get like a single quantity flow which routes a bipartite graph, and then do we have like an analog of that statement where like an expander plus like that thing is still an expander?
Yeah.
Sparse, right? Like the argument, I mean, the argument still works as long as it's like a sparse bipartite graph, right, along the boundary.
So
Maybe.
Because like you don't increase the, I guess.
yeah, like so as long
Yeah,
as
different constant than 3, but
Yeah.
as long as you have some expander here, and then there is some, this is not quite matching, but bipartite graph, and let's say this bipartite graph kind of respect the degree of x.
Yeah, that's basically what I was asking.
yeah. Then like that just generalize what you did in the homework. Yeah. Okay. Like and yeah, the quality might get worse by a factor 3. Okay, good. So we are done inside the core. Okay. So now it's about like how to route the rest to the battery. Forward it to the battery. So forwarding to the battery, we need two things. First, we need that this forwarding don't take too much congestion inside H. That's the first thing, always have. But we also have another one, which is when we forward some, like delegate the task to my own battery, like the load at my battery don't increase too much. Like it used to be this much load, and it should be at most this much load after I forward to the battery. Okay. So the load don't increase too much. Okay. So let's first consider the demand pairs with one endpoint like in H, but not between the inside the core. How many types can there be? Well, there is a type where like I said that there is two types. One is just one point is inside outer child, and another point is outside the core. So maybe like here, or just in outside the core. That's the first type. Okay, this is like the first type. Maybe this two. Yeah. Another type is just one is inside the core, and another pair is like outside the core. So maybe like from A prime, B prime here, or A prime to C prime outside. Okay. So I just separate them into these types. Okay. So we take care of each of these types separately. Let's consider this first type. When one endpoint is out in the outer child and another one is outside the core. Okay. So let's say that H child is the outer child. Okay. Then you actually can see that the battery of H child is kind of, this is H child. You have two parts. I call this, there is like kind of this part. I call this midway battery. And this part is the goal battery. Okay. So what we have so far is that now like consider the demand pairs where at least one endpoint is inside HR. Like what's the task that we need to do? So in the beginning, some flow has been sent to the battery of HR. Okay. So it can be on the midway battery or the goal battery, midway battery and the goal battery. And the load here is like alpha I. The flow to this guy is alpha I. Okay. And our goal is quite simple. I just want to forward everything to the goal. Like the flow shouldn't finish at the midway battery. It should just go to the goal here. Okay. Good. But this is going to be quite simple. Why? Because we actually know that from this midway battery, there exists a flow that each of these guys send one unit. And each of these guys, like, and every one here receive at most 1 over log. Right? Just from the structure of max flow. This is the min cut. So there is a flow that saturates these red edges and respect the purple edges with capacity 1 over log. Okay. So how do we, once we know that there is such a flow, what do? We just, like whatever the load that, like whatever flow path that have come to this one, just follow this flow, this purple flow. Just concatenate them by the purple flow to the goal. Okay. So there is this flow inside the outer children that saturate midway battery and respect 1 over log. This thing. And if I just forward it to the goal, I have 2 questions. What's the congestion in forwarding this? And next, how much does the load here increase? What's the congestion first?
Isn't it congestion 1 because this is just coming from max flow?
If I just want to send each of these guys want to send just 1 unit, then the congestion here would be just 1. But here I might not want to just send 1 unit because the load, like the flow that get to this guy so far can be as big as alpha I. So I can just basically scale up the flow by alpha I at most and just send following this flow. So the congestion is not 1, but just alpha I, small. Okay. It's not even log, it's just constant. How much the load on the goal battery increase? How much does it increase?
Or no, alpha I over log n.
Alpha I over log n. Yeah. Okay. Makes sense? So it's quite simple. Like this part, you have send flow to the battery of the red cluster so far. But I know that one part of the battery can forward it to this part with low congestion. And it's just gonna increase the congestion by like 1 over log fraction. So that's good. Okay. So just by following this flow, we can send all the mass from every edge in the midway battery, each of load at most alpha, to the goal battery so that the load increased by alpha I times 1 over log. This can take congestion alpha I inside HI. Okay. So that's the first part. If one endpoint is inside the outer child and outside the core, just forward it to the battery. That's easy. Okay. So next is when one endpoint is inside the core, okay, and we want to send it to, like we want to forward this to the battery. Okay. Okay. So consider all demand pairs where only one endpoint is inside the core. Another endpoint maybe like here or here, okay, outside the core. But again, note that I don't try to send flow. I just try to forward it to the battery here. Okay. So again, what we have so far is that we have partially route the flow up to the battery edges of inner children. So, which is battery of the core, basically. Actually, no, sorry. I might have route to this thing or to the battery of the core. Okay. But the goal is to route from the battery of these children to the battery of H. And also the load of H should increase by at most alpha I times log 1 over log. Okay. So the strategy is here. I'm just gonna send first. I said that I will just try to send to the battery of the core first. Okay. Whatever this thing, if it ends here, I just send to the battery of the core first. Okay. Kind of forward it to the battery of the core. Not quite yet the battery of H, but just battery of the core. And the load at the core when I forward should have load just actually at most 1. And why I can do this? Well, because you know that like it kind of, so far I forward I have the flow or at F in or the battery of the core. And I just want to send to the core, a battery of the core. But F in and the battery of the core we've seen before that they are expanding. Okay. So I can route to the battery of the core with this congestion. Just because the battery of the core and F in, they are expanding. Are we good? Trying to send from F in to the battery of the core. This defines the demand that respect this thing, like the source kind of respect like alpha I and this union F in and the sink respect this is battery of core. Respect the battery of the core. So this just respect both of this set, but this thing is expanding, so you can route with low congestion. So you get to battery of the core. So you get to the battery of the core with low congestion. Maybe here and here. If it ends here, it ends at the boundary of H, then you're done. The load here is at even 1. Okay? Actually, sorry. Actually, I mean, the load here will be alpha. Actually, I should say that, sorry. If it ends here, the load here is like gamma, 1/log. Because, yeah. But if it ends here, the load is 1. So if it ends at here, you just increase the load by 1/log. If it ends on the red edges, what should you do? Just do the same thing we have done. Just forward it further to, this is just a midway battery. And you know how to forward it to the goal battery. Just use the same strategy we have used. And to forward from here to here, that increase the load by 1/log again. Okay. So I kind of, I'm a bit quick here, but are we good? So let me conclude quickly. So we have just like complete the tasks inside the core with low congestion, okay? And the rest we send to the battery with low congestion, and we increase the load by something like 1 plus 1/log factor. Yeah, that's why everything is done. Okay, so yeah, we're gonna finish it for now. Actually, let me mention one thing. There's another paper that built this 3-flow Sparsifier with Polylog quality. The difference is that this construction is bottom up, and it's based on expanded decomposition, which is bottom up, instead of expanding balance operator, which is kind of top down, kind of orthogonal from what I present today. And the bottom up approach has some advantage, but I will not talk about this advantage today. Okay. All right, so that's it for today. So that's kind of finished the first half of the course. Okay, see you tomorrow.